So one of the assignments in class was this one, which is also going to be part of your homework, and it does require a derivation in calculus. So in this question, and again, they're not going to have you do this on an AP exam. At the very least, they'll ask you to write a differential equation, but it's good to get it in practice. And like I said, I'm giving you practice on things that are harder than what you'll see on an AP exam, so that when you see it, writing a differential equation will seem very, very easy. So here we have a object of mass m that's moving where there is a resistive force negative kV. Kv is a constant, and v is velocity, and the gravitational force exerted on this object is negligible. So this is one thing that we kind of practiced with so often, is the force of gravity and the resistive force opposing each other. So this is the one scenario where they're telling us there's no gravitational force. And I know students in class were trying to solve it with and thought it was a very hard problem, but now we're going to solve it without, which makes it very easy. The second thing we want to point out is that the initial velocity is not zero, it's actually v naught. So how would we express our function of v? An expression for v is a function of time for this scenario. So the first thing we're going to do, and you should always start with this, and this is why we mess up on this in class, is that when we read the question, there's no gravitational force. We can say that the resistive force, let's say the object is moving to the left, the resistive force is negative kV to the right, and that's the only force acting on it. So in this scenario, this is our net force, which is equal to MA. And then from there, we're going to write it as a differential equation. So if on an AP exam, this is generally what they're going to ask you, is to write it as a differential equation, this is where you would stop. Acceleration is dv over dt. You can think about it as a small change in velocity over a small change in time, and that would suffice for a differential equation to represent velocity, the velocity of this object. Okay, but because we're getting some extra practice and it's good to challenge ourselves, we're going to go ahead and solve this. In this scenario, I want my velocity here and my dv to be together. So I'm going to bring all my constants, my mass here, and my dt to the other side. So what that does is it gives me negative k dt over m, and I'm putting all my constants to the left just because I know it's going to look nicer when I integrate. And then I have 1 over v dv, and then I'm going to integrate both sides. Now that I have dt and dv on one side, I can integrate both sides. And for this scenario, at time equals 0, initial velocity is v naught. And at some point in time t, velocity is v. So those are our limits. The integral of dt is just t, but if you need to work that out in your head, you can think about it as the integral of t to the 0 dt, which is adding 1 to the power and dividing by 1. So that's just t. And then I'm going from the limits of t to 0, which is t minus 0. And in the end, that just leaves you with t. I didn't forget about this constant here. Everything is multiplied by this constant. And I'm not going to rework this out. You guys know that it's just that on the right side. But let's work out the left side. This is an integral you want to know. The integration of 1 over v dv is ln. And we're going from v to v naught, which gives me ln v minus ln v naught. You guys are very familiar, I'm assuming, because you just worked with this stuff, but the property of ln, when you subtract two ln's, is that you could turn them into a fraction. And then from there, we can get rid of ln by taking e to both sides. And then I get e to this ugly power, but you know what? That's okay, is v over v naught, and then our velocity. If I isolate that, I've got v naught on the multiplied by e to the negative k over m times t. So this is our answer, and that gives us A.